Right now, as you sit here watching this video, something is hurtling through the blackness of space. It has no consciousness, no intent, no malice. It is simply a rock, or perhaps a chunk of iron and nickel, tumbling end over end in the silent void between planets. It could be the size of a car, it could be the size of a mountain, and it might be heading directly toward the pale blue dot we call home. The terrifying part is not that such objects exist. The terrifying part is that we might not see it coming until it is far, far too late. You see, space is not the peaceful, serene canvas that photographs make it appear. Space is a shooting gallery. It always has been. And Earth, our fragile little world, is sitting right in the middle of it, protected by nothing more than a thin envelope of gas and an invisible magnetic shield that, as we will discover later in this video, is actually weakening as we speak. The dinosaurs ruled this planet for 165 million years. They were the most successful large animals in Earth's history. They survived volcanic eruptions, shifting continents, and dramatic climate swings. And then, on one ordinary afternoon, 66 million years ago, a rock from space ended everything. They had no telescopes, they had no warning systems, they had no space agencies scanning the skies. They simply looked up, and the sky was on fire. You, however, have something the dinosaurs never did. You have knowledge, you have awareness, and you have this video. Because today, we are going to go through every single real, scientifically documented, and thoroughly researched way that our planet could face catastrophic destruction. This is not science fiction. This is not Hollywood. This is not speculation or fantasy. Everything you are about to hear is based on real physics, real geology, real astronomy, and real data from organizations like NASA, the European Space Agency, the United States Geological Survey, and peer-reviewed scientific journals. Some of these threats have already struck Earth before. Some of them are happening right now, at this very moment. And some of them are so terrifying that even the scientists who study them admit they lose sleep thinking about the implications. So before we begin this journey through the most dangerous phenomena in the known universe, I need you to do something for me. If you are the kind of person who is genuinely curious about the universe, if you are the kind of person who wants to understand the real science behind the biggest questions, then hit that subscribe button right now. Turn on notifications, and drop a comment below telling me which cosmic threat you think is the most dangerous. I want to see your answer now, and I want to see if it changes by the time we reach the end of this video. Because I promise you, by the end of what you are about to watch, your perspective on our place in this universe will never be quite the same again. Let us begin with the one threat that has already proven, beyond any shadow of doubt, that it can end life on Earth. Let us begin with the rocks falling from the sky. 66 million years ago, the Earth was a very different place. The continents were in different positions. The climate was warmer, and the planet was dominated by creatures that had evolved into an astonishing diversity of forms over tens of millions of years. Tyrannosaurus rex stalked the forests of what is now North America. Pterosaurs, with wingspans wider than a small airplane, soared over warm, shallow seas. In those seas, ammonites, those beautiful spiral-shelled relatives of the modern nautilus, drifted in their billions. Triceratops grazed on ferns and cycads. Small, furry mammals scurried in the underbrush, living in the shadows of giants, waiting for an opportunity that they did not yet know was coming. And then, without any warning whatsoever, a piece of rock roughly 10 kilometers across, about the size of Mount Everest, entered Earth's atmosphere at a speed of approximately 20 kilometers per second. That is 72,000 kilometers per hour. That is 44,000 miles per hour. To put that in perspective, a bullet fired from a high-powered rifle travels at roughly 1 kilometer per second. This asteroid was moving 20 times faster than a bullet. It punched through the atmosphere in less than 1 second. There was no time for the air to get out of the way. The compression of the atmosphere in front of the asteroid heated it to temperatures hotter than the surface of the sun. And then it hit. The impact site was what is now the Yucatan Peninsula of Mexico, near the modern town of Chicxulub. The asteroid struck a shallow sea underlain by limestone and sulfur-rich rock, and in that instant, it released energy equivalent to more than 100 million megatons of TNT. Let me help you understand what that number means. The atomic bomb dropped on Hiroshima in 1945 released energy equivalent to about 15 kilotons of TNT. The Chicxulub impact released the energy of more than 6 billion Hiroshima bombs. 6 billion, not 6 million. 6 billion. In one instant, the rock at the impact site did not merely crack or shatter, it vaporized. Solid rock turned directly into superheated gas in a fraction of a second. A crater more than 180 kilometers across, that is over 90 miles, was gouged into the Earth's surface. Inside the crater, a ring of mountains formed from the rebounding rock, a feature geologists call a peak ring, as material that had been blasted downward surged back upward, like the splash when you drop a stone into water. Except this splash was made of liquefied rock, and it reached heights of several kilometers. In 2016, an international team of scientists drilled into the peak ring of the Chicxulub crater and extracted core samples that allowed them, for the first time, to reconstruct a detailed timeline of what happened in the hours and days after impact. This research, led by geologist Sean Gulick of the University of Texas at Austin, was published in 2019 in the Proceedings of the National Academy of Sciences, and the findings are nothing short of extraordinary. Within the first minutes of the impact, over 70 feet of melted rock piled up on the peak ring as material that had been liquefied by the heat of the impact settled back down. The energy of the collision sent shockwaves rippling through the Earth's crust, triggering earthquakes of a magnitude never experienced in human history. The sea was violently displaced, and within minutes, enormous surges of water began rushing back into the newly formed crater. These surges carried with them an additional 260 feet of melted stone, sand, and debris, piling layer upon layer of destruction into the geological record. And then, perhaps an hour or two after the initial impact, a tsunami arrived. Not a wave generated by the impact itself, but the reflected wave, the wall of water that had raced outward from the crater, struck distant coastlines and bounced back. This reflected tsunami deposited another distinct layer of sediment within the crater, a layer containing gravel, sand, and something else. Charcoal, burned wood, the remains of forests that had been set on fire hundreds of kilometers inland by the heat of the impact. Because here is what happened in those first hours across the planet. The impact ejected an unimaginable quantity of rock and dust into the atmosphere and even into space. As this debris rained back down through the atmosphere, friction heated it to incandescent temperatures. The entire sky across much of the planet began to glow. It was as if the atmosphere itself had caught fire. Gulick and his colleagues found that this radiant heat pulse would have raised temperatures enough to ignite vegetation at distances of more than 900 miles from the impact site. At greater distances, the falling debris caused additional fires through frictional heating. Forests burned across entire continents. The fires were then doused by the devastating waves that swept inland, and the charred remains of those forests were washed back out to sea, eventually settling in the crater itself, where they were found 66 million years later in a drill core. But the fires and the tsunamis were not what killed most of the life on Earth. It was what happened next. The rocks that the asteroid struck were rich in sulfur. When those rocks vaporized, enormous quantities of sulfur were injected into the upper atmosphere. There, the sulfur combined with water vapor to create a dense haze of sulfate aerosols, tiny droplets of sulfuric acid that spread across the entire globe and blocked sunlight for years. Temperatures plummeted. Photosynthesis, the process by which plants convert sunlight into food, effectively stopped. The base of the food chain collapsed. On land, plants died. The herbivores that depended on those plants died. The predators that depended on the herbivores died. In the oceans, phytoplankton, the microscopic organisms that produce most of the world's oxygen and form the foundation of the marine food web, perished in staggering numbers. The entire biosphere entered a state of collapse that lasted years, possibly decades. As Gulick himself described it, first you burned parts of the continents, and then you had global dimming of the sun and plummeting temperatures for years to follow. The result was the Cretaceous Paleogene mass extinction, the fifth and most recent of the so-called Big Five mass extinctions in Earth's history. 75% of all species on Earth went extinct. Every non-avian dinosaur vanished. The pterosaurs disappeared. The ammonites, those ancient mariners that had survived multiple previous extinction events, were wiped out completely. Marine reptiles like mosasaurs and plesiosaurs were gone. Even among the survivors, losses were catastrophic. Lizards, snakes, mammals, birds, fish, and insects all suffered devastating reductions in diversity. And here is the detail that should make you sit up and pay very close attention. Gulick's research showed that the severity of the extinction was partly determined by where the asteroid happened to hit. The sulfur-rich rocks of the Yucatan were uniquely dangerous. Had the asteroid struck a different part of the planet, say a region with different geology or deeper ocean, the sulfate aerosol effect might have been dramatically reduced. The extinction might have been less severe. It might not have happened at all. The location of impact was, in a very real sense, the worst possible luck for the dinosaurs. This tells us something important. It is not just the size of the impactor that matters. It is also where it hits, what kind of rock it strikes, at what angle it arrives, and what the planet's geology and climate are like at the time. The Chicxulub event was a perfect storm of destructive factors, and it reshaped the entire trajectory of life on Earth. Everything that happened afterward, the rise of mammals, the evolution of primates, the emergence of human beings, all of it traces back to that one catastrophic afternoon, 66 million years ago. Now you might be thinking, that was 66 million years ago. Surely impacts like that are incredibly rare. And you would be right. Chicxulub-scale impacts happen roughly once every 100 million years on average. But here is what most people do not realize. Earth is hit by objects from space far more frequently than you might imagine. NASA estimates that car-sized asteroids enter Earth's atmosphere and burn up roughly once a year. Objects the size of a football field strike approximately every 2,000 years. And events large enough to cause regional devastation, like the one that flattened a Siberian forest in 1908, happen perhaps once every few hundred years. Let me tell you about that Siberian event, because it is one of the most remarkable and frightening natural events in modern history. On June 30th, 1908, something entered the atmosphere above a remote region of Siberia near the Podkamennaya Tunguska River. To this day, we are not entirely sure whether it was a small asteroid or a fragment of a comet. What we do know is that it exploded approximately 5 to 10 kilometers above the surface, in what is called an airburst. The explosion released energy estimated at 3 to 50 megatons of TNT, with most scientific estimates centering around 12 megatons. That is roughly 800 times the energy of the Hiroshima bomb. The shockwave flattened 2,150 square kilometers of forest. That is 830 square miles. 80 million trees were knocked down, their trunks all pointing radially outward from the blast center, like the spokes of an enormous wheel of destruction. The pressure wave was recorded on barometers across Europe. Seismic stations around the world detected the impact. In London, more than 5,000 kilometers away, the night sky glowed so brightly from atmospheric disturbance that people could read newspapers outdoors at midnight. And here is the detail that should send a chill down your spine. If the Tunguska object had arrived 4 hours and 47 minutes later, the rotation of the Earth would have placed the city of St. Petersburg directly beneath it. A major European city would have been completely destroyed in 1908, and the course of human history would have been dramatically altered. Now let us jump forward to something that happened much more recently, and that you may actually remember if you were alive in 2013. On February the 15th of that year, a rock approximately 18 meters across, about 60 feet, weighing roughly 9,100 tons, entered Earth's atmosphere above the Russian city of Chelyabinsk. It was traveling at 19.16 kilometers per second, which is 68,000 kilometers per hour, and it came in at a shallow angle of about 18 degrees. The friction with the atmosphere heated it to incandescent temperatures, and approximately 29.7 kilometers above the surface, it exploded. The airburst released energy equivalent to roughly 500 kilotons of TNT, about 30 times the Hiroshima bomb. The shockwave that followed was devastating. Windows shattered across the city and surrounding towns. Over 7,200 buildings in 6 cities were damaged. More than 1,500 people were injured, mostly by flying glass from shattered windows. People who happened to be looking at the sky saw a fireball brighter than the sun streaking across the morning sky, followed by a blinding flash, followed by a thunderous shockwave that arrived minutes later. And here is the fact that genuinely alarmed the world's space agencies. No one saw it coming. Not a single telescope on Earth, not a single satellite in orbit, not a single space agency on the planet detected the Chelyabinsk asteroid before it hit. It approached Earth from the direction of the Sun, which is a massive blind spot for ground-based telescopes. We cannot look toward the Sun to search for asteroids, because the Sun's glare blinds our instruments. The Chelyabinsk meteor was a wake-up call. It demonstrated that objects large enough to cause significant damage and injury can arrive without any warning whatsoever, and that our detection capabilities have dangerous gaps. This is not a theoretical problem. This actually happened in the modern era to a major city, and no one saw it coming. So let us talk about what is out there right now. What are the specific objects that scientists are tracking? And how worried should we be? Let me introduce you to asteroid 99,942 Apophis, and I want you to pay very close attention, because what I am about to tell you is not speculation. It is confirmed by NASA, the European Space Agency, and every major astronomical observatory on Earth. Apophis was discovered in 2004, and when astronomers first calculated its orbit, they got a result that made headlines worldwide. There was a 2.7% chance that Apophis would hit Earth in 2029. Now, 2.7% might not sound like a lot, but for an asteroid of this size, it was an extraordinarily high probability. Apophis is approximately 370 meters across, that is 1,210 feet. It is roughly the size of the Eiffel Tower. If an object that size hit the Earth, the energy released would be equivalent to approximately 1,100 megatons of TNT, enough to destroy an area the size of a small country and cause global climate effects. After Apophis was discovered, astronomers around the world turned their telescopes toward it and gathered more precise measurements of its orbit. And the good news is that with these better data, the 2029 impact scenario was ruled out. Apophis will not hit Earth in 2029. But here is what will happen, and this is confirmed as of the latest NASA and ESA data available. On April 13th, 2029, asteroid Apophis will pass just 31,600 kilometers from Earth's surface. That is approximately 19,600 miles. To give you a sense of how close that is, the satellites that provide your television signal, your weather data, and your GPS navigation orbit Earth at geostationary altitude, which is about 36,000 kilometers. Apophis will pass closer to Earth than those satellites. It will be visible to the naked eye from parts of Europe, Africa, and Western Asia, appearing as a moderately bright star moving rapidly across the sky. This will be the closest approach of an asteroid this large ever predicted in advance in the history of human civilization. Scientists will use this unprecedented opportunity to study a near-Earth asteroid up close, gathering data that will be invaluable for planetary defense. And NASA has confirmed that Apophis poses no risk of impact for at least the next 100 years. But Apophis is not the only object on our radar. Let me tell you about asteroid 101,955 Bennu. Bennu is special because we have actually been there. NASA's OSIRIS-REx mission traveled to Bennu, orbited it for over 2 years, and collected samples from its surface that were returned to Earth in September of 2023. We have pieces of Bennu in our laboratories right now, and what we learned from studying Bennu is both fascinating and sobering. Bennu is 490 meters wide, about 1,610 feet, slightly larger than the Empire State Building is tall. It is what scientists call a rubble pile asteroid, not a single solid rock, but a loose collection of boulders, pebbles, and dust held together by gravity and very weak cohesive forces. This is important because it affects how we might try to deflect it if we ever needed to. And we might need to. Astronomers have calculated that Bennu has a cumulative probability of approximately 1 in 2,700 of impacting Earth on September 24th, 2182. That is a 0.037% chance. In February of 2025, Reuters reported on a study by scientists who modeled the potential devastation of a Bennu impact. The results showed that a collision would create a crater roughly 5 kilometers wide, with city-level destruction extending for hundreds of miles in every direction. If it struck an ocean, it would generate tsunamis capable of devastating coastal cities around the entire basin. And the global climate effects, from dust and debris injected into the atmosphere, would cause agricultural disruptions worldwide. Now, I want to tell you about a very recent event that most people are not even aware of, because it happened fast, and it was resolved before it could make major headlines. In late 2024, astronomers discovered a small asteroid designated 2024 YR4. This object is estimated to be 40 to 90 meters in diameter, roughly the size of the Chelyabinsk meteor, or somewhat larger. When its orbit was first calculated, the results were alarming. By February 18, 2025, the estimated probability of 2024 YR4 impacting Earth in 2032 had risen to 3.1%. That was the highest impact probability ever recorded for a newly discovered asteroid of that size. For a few tense days, this asteroid held the highest rating ever on the Palermo Technical Impact Hazard Scale, a logarithmic scale that scientists use to assess the severity of impact threats. Astronomers around the world scrambled to make additional observations, refining the orbit calculation. And gradually, as more data came in, the probability dropped. By February 23rd, it had fallen to 0.26%. By the time the observation campaign was complete, it had dropped to 0.004%, effectively ruling out an impact. NASA officially confirmed that 2024 YR4 will safely pass Earth in 2032. But this episode is incredibly important because it shows you what a real asteroid scare looks like in the modern era. For several days, the best calculations available to humanity said there was roughly a 1 in 32 chance that a city-destroying asteroid would hit Earth in 7 years. That is not a drill. That is not a movie. That happened. And the fact that additional observations ruled it out does not diminish the significance of those initial calculations. It shows that the threat is real, that new asteroids can appear at any time, and that sometimes the initial data is genuinely alarming. So, what are we doing about it? For the first time in the 4.5 billion year history of our planet, one species has developed the ability to potentially prevent an asteroid impact. On September 26, 2022, NASA's DART mission, the Double Asteroid Redirection Test, deliberately slammed a spacecraft into Dimorphos, a 160-meter-wide moonlet orbiting the larger asteroid Didymos. The goal was simple but unprecedented: change the orbit of an asteroid by hitting it with a spacecraft. And it worked. DART changed the orbital period of Dimorphos by 33 minutes, reducing it from 11 hours and 55 minutes to 11 hours and 22 minutes. This far exceeded the minimum benchmark of 73 seconds that NASA had set as a success criterion. Furthermore, the impact changed the physical shape of Dimorphos and sent huge boulders flying off its surface, demonstrating that the energy transfer was even more effective than models had predicted. This was the first time in history that humanity deliberately and measurably altered the trajectory of a celestial body. The European Space Agency's Hera mission, launched in October 2024, is now on its way to the Didymos-Dimorphos system to conduct a detailed post-impact survey. And NASA is developing NEO-Surveyor, a next-generation space telescope specifically designed to find potentially hazardous asteroids, including those that approach from the direction of the Sun, the blind spot that allowed the Chelyabinsk meteor to arrive undetected. There is also the Sentry system, operated by NASA's Jet Propulsion Laboratory, an automated collision monitoring system that continuously scans the most current asteroid catalogue for possibilities of future impacts with Earth. But here is the honest truth. We have demonstrated that we can deflect a small asteroid with years of warning. That is an extraordinary achievement. But a large asteroid detected with only weeks or months of warning, or an object approaching from the Sun's direction that we never see coming at all, that remains a scenario for which we currently have no adequate defense. The sky is being watched, but it is not being watched perfectly. Now I want to take you away from the cold vacuum of space and bring you to something much closer to home, something that is not above us, but beneath us, something that has been building pressure for hundreds of thousands of years, and that new scientific research published just weeks ago suggests may be more dangerous than we previously understood. I want to talk about the ground you are standing on, because underneath the serene beauty of one of America's most beloved national parks, there is a monster. Let us talk about Yellowstone. When you visit Yellowstone National Park, you see something magical. Geysers erupting with clockwork regularity, hot springs in stunning shades of blue, green and orange, bubbling mud pots, steaming fumaroles. It is one of the most geothermally active places on Earth, and tourists come from around the world to marvel at its beauty. But very few of those tourists realize that they are standing inside a volcano. Not on a volcano, inside one. The Yellowstone caldera is a volcanic crater approximately 72 kilometers by 55 kilometers. That is 45 miles by 34 miles. It is so enormous that it was not even identified as a volcanic feature until satellite imagery became available in the late 20th century. From the ground, you cannot see it. It is too big. The hills and ridges around you are the walls and rim of a crater that was created by an eruption so massive that it defies human comprehension. Underneath this caldera, according to data from the United States Geological Survey, updated as recently as May 2025, there are 2 magma bodies. The shallower one is composed of rhyolite, a high silica rock, and it stretches from 5 kilometers to about 17 kilometers beneath the surface. It is approximately 90 kilometers long and 40 kilometers wide. Let me say that again so it sinks in. The shallow magma chamber beneath Yellowstone is 55 miles long and 25 miles wide. However, before you panic, it is important to understand that this chamber is mostly solid rock. Only about 5 to 15% of it is actually molten. The deeper reservoir is composed of basalt and extends from 20 to 50 kilometers below the surface. This deeper chamber is about 4.5 times larger than the shallow one, but it contains only about 2% melt. Scientists image these structures using a technique called seismic tomography, which is essentially a CT scan of the Earth using earthquake waves instead of X-rays. Hundreds to thousands of earthquakes are recorded by dozens of seismograph stations, and the speed at which seismic waves travel through the rock reveals the temperature, composition, and melt fraction of the material below. Yellowstone has produced 3 supereruptions in the past 2.1 million years. The first, the Huckleberry Ridge eruption, occurred approximately 2.1 million years ago and ejected about 2,500 cubic kilometers of material. The second, the Mesa Falls eruption, occurred about 1.3 million years ago and was smaller, ejecting about 280 cubic kilometers. The third, the Lava Creek eruption, occurred roughly 640,000 years ago and ejected about 1,000 cubic kilometers. To understand the scale, recall that the 1980 eruption of Mount St. Helens, which killed 57 people and was considered a major volcanic disaster, ejected about 1 cubic kilometer of material. The Lava Creek eruption ejected 1,000 times that amount. Now, you've probably heard people say that Yellowstone is overdue for an eruption. This is one of the most persistent and misleading myths in popular science. The average interval between the 3 known supereruptions is about 725,000 years. The last one was 640,000 years ago, so simple arithmetic might suggest we are getting close. But the United States Geological Survey has been very clear on this point, and I am going to quote them directly. Yellowstone is not overdue for an eruption. Volcanoes do not work in predictable ways, and their eruptions do not follow predictable schedules. The 725,000-year average is based on just 2 intervals between 3 eruptions. Drawing conclusions from 2 data points is statistically meaningless. The probability of a supereruption at Yellowstone in any given year is estimated at roughly 1 in 730,000. However, and this is important, new research published in April 2026 has revealed something that has genuinely stirred the scientific community. A team from the Institute of Geology and Geophysics of the Chinese Academy of Sciences published a study in the journal Science that challenged previous assumptions about how supervolcanoes work. Previous research suggested that supervolcanoes harbored large, deep magma chambers that slowly accumulated molten rock until the pressure became too great and triggered an eruption. The problem was that when scientists actually looked for these large, deep reservoirs beneath known supervolcanoes, they were conspicuously absent. The new study used a comprehensive 3-dimensional model of the lithosphere and asthenosphere beneath western North America to investigate the engine that drives Yellowstone. What they found was surprising and, to some, unsettling. The eruption mechanism is not driven by a deep reservoir at all. Instead, large, sprawling zones of partially molten rock, what scientists call magma mush systems, permeate much of the lithosphere at surprisingly shallow depths. Magma originates in the upper asthenosphere, the hot and slow-flowing layer beneath the Earth's rigid outer shell, and ascends into the lithosphere, where it mixes with surrounding solid rock to form a viscous magma mush. Meanwhile, a hot rock flow is steadily moving eastward beneath the caldera, ripping apart the hard rock of the lithosphere and creating channels through which molten material can rise and fill the volcano's mush reservoir. The implication of this finding is that a supervolcano can replenish its magma supply through tectonic activity alone, without needing a massive deep chamber. This challenges our understanding of how quickly a supervolcano can reload between eruptions. It does not mean that Yellowstone is about to erupt, but it does mean that our previous models of how long it takes for a supervolcano to become dangerous again may need to be revised. Now, what would actually happen if Yellowstone produced another super eruption? Based on USGS modeling and scientific literature, the effects would be catastrophic on a scale that is difficult to fully grasp. Pyroclastic flows, those superheated avalanches of gas, ash, and rock that race across the landscape at hundreds of kilometers per hour, would devastate everything within roughly 60 to 100 kilometers of the caldera. Nothing survives a pyroclastic flow. Not buildings, not vehicles, not people. Everything in the path is incinerated, buried, and crushed. Beyond the immediate devastation zone, heavy ashfall would blanket much of the western and central United States. We are talking about feet of ash, not inches. This volcanic ash is not like the soft ash from a campfire. It is composed of tiny, jagged fragments of rock and glass. It is abrasive, it is heavy when wet, and it is devastating to machinery, electronics, water supplies, and lungs. The agricultural heartland of the United States, the Midwest breadbasket that feeds hundreds of millions of people, could be buried. The economic damage has been estimated at more than $3 trillion. But the truly global effects would come from the volcanic winter. Massive quantities of sulfur dioxide injected into the stratosphere would form a sulfuric acid aerosol that would circle the globe and block sunlight for years. Global temperatures could drop by several degrees Celsius. Growing seasons would shorten, crops would fail, famine would spread across the world. And while we are discussing supervolcanoes, I want to mention something that I think deserves far more attention than it gets. Campi Flegrei, a supervolcanic caldera in southern Italy, sits directly beneath the western outskirts of the city of Naples. 3 million people live inside and around this caldera. Campi Flegrei has been experiencing increased seismic activity and ground uplift, a phenomenon called bradyseism, in recent years. The ground in some areas has risen by several meters over the past few decades. This caldera is arguably a more immediate concern than Yellowstone, not because a super eruption is imminent, but because the population density directly on top of the volcanic system makes even a smaller eruption potentially catastrophic. Let me also take you back 74,000 years to the most powerful volcanic eruption of the last 2 million years. Lake Toba, on the island of Sumatra in Indonesia, is a beautiful, tranquil body of water, roughly 100 kilometers long. It is the largest volcanic lake in the world, and it fills the caldera of a supervolcano that 74,000 years ago produced an eruption that dwarfs anything in human recorded history. The Toba eruption ejected approximately 2,800 cubic kilometers of material. To visualize that, imagine burying the entire Indian subcontinent, the entire landmass of India, under 5 centimeters of volcanic ash. That is what Toba did. The eruption injected colossal quantities of sulfur dioxide into the stratosphere, triggering a volcanic winter that may have lasted 6 to 10 years, during which global temperatures dropped by 3 to 5 degrees Celsius. Some geneticists have proposed what is known as the Toba catastrophe theory, the hypothesis that this eruption reduced the entire human population on Earth to somewhere between 3,000 and 10,000 breeding individuals. This would explain why modern humans have remarkably low genetic diversity compared to other great apes, despite our large population. We are, genetically speaking, a very homogeneous species, and some scientists believe this bottleneck, caused by Toba, is the reason. However, I must be honest with you about the current state of the science. This hypothesis is debated. Paleoanthropologist John Hawkes and other researchers have argued that the genetic evidence for a population bottleneck does not clearly align with the timing of the Toba eruption. Archaeological sites in Africa and India show that some human populations appear to have survived relatively intact through the eruption period. The truth is likely more nuanced than either extreme. Toba was undoubtedly a devastating event, but whether it nearly drove our species to extinction remains an open scientific question. What is not in question is that supervolcanic eruptions are among the most destructive natural events that can occur on this planet. Now, I want to take you somewhere completely different. I want to take you to the source of all life on Earth, and simultaneously, one of the greatest threats to our survival. I want to talk about the sun. Every second of every day, the sun bathes our planet in light and warmth. Without it, Earth would be a frozen, lifeless ball of rock drifting in the darkness. The sun drives our weather, powers photosynthesis, and makes all known life possible. But the sun is not a gentle, benevolent companion. It is a thermonuclear furnace, a sphere of superheated plasma 1.3 million times the volume of Earth, with a core temperature of 15 million degrees Celsius. And sometimes, it lashes out. On September 1st, 1859, a British astronomer named Richard Carrington was observing the sun through a filtered telescope at his private observatory when he witnessed something extraordinary. A brilliant white flare erupted from the surface of the sun, so bright that it was visible even against the blinding solar disk. Carrington carefully recorded his observations, not knowing that he was witnessing the precursor to the most intense geomagnetic storm in recorded history. Approximately 17 hours later, the blast from that solar eruption reached Earth. What had happened was this: the sun had unleashed a coronal mass ejection, or CME, a massive expulsion of plasma and magnetic field from the solar corona. Billions of tons of charged particles traveling at millions of kilometers per hour slammed into Earth's magnetosphere, the magnetic bubble that normally protects our planet from solar radiation. The magnetosphere compressed and buckled. Charged particles poured into the upper atmosphere along magnetic field lines, and the result was an aurora, a display of northern and southern lights of unprecedented scale and intensity. Normally, auroras are visible only near the poles, in places like Norway, Canada, and Antarctica. During the Carrington Event, auroras were seen as far south as Colombia, Hawaii, and the Caribbean. People in the northeastern United States could read newspapers at midnight by the light of the aurora, so bright was the glow. The sky turned vivid shades of red, green, and purple across most of the planet. But the beauty of the aurora masked something far more concerning. The geomagnetic storm induced powerful electrical currents in every long conductor on Earth. In 1859, the most advanced electrical technology was the telegraph, and telegraph systems worldwide went haywire. Operators received painful electric shocks from their equipment. Sparks flew from telegraph machines, setting paper on fire. And most remarkably, in some cases, telegraph operators disconnected their batteries entirely and found that their machines continued to operate powered solely by the electrical currents induced by the geomagnetic storm. The Earth itself had become a battery. Now, in 1859, this was dramatic and alarming, but the consequences were limited, because the most complex electrical technology in the world was a copper wire strung between wooden poles. Think about what the world looks like today. Our entire civilization runs on electricity. The power grid, the internet, telecommunications, banking, water treatment, hospitals, traffic systems, supply chains, military systems, satellites, GPS navigation, air traffic control, weather forecasting, and virtually every other system that keeps modern society functioning depends on electrical infrastructure and electronics that did not exist in 1859. What would a Carrington-class geomagnetic storm do to our world today? The answer, according to scientists and risk analysts who have studied this question extensively, is terrifying. The primary danger is to high-voltage transformers, the massive, custom-built pieces of equipment that form the backbone of the electrical grid. During a severe geomagnetic storm, geomagnetically induced currents flow through the ground and into the grounding wires of these transformers. The transformers are not designed to handle DC current, and these induced currents can overheat and permanently destroy them. Here is the critical problem. These transformers are not mass-produced. They are custom-built for each installation. They weigh hundreds of tons. They cost millions of dollars each, and they take 12 to 18 months to manufacture and deliver. A Carrington-class storm could destroy hundreds of high-voltage transformers simultaneously across an entire continent. If that happened, large portions of the power grid would not come back online for months or years. Think about what that means. No electricity means no running water, because water treatment plants and pumping stations require power. No electricity means no fuel, because gas pumps require power. No electricity means no refrigeration, which means food spoilage begins within hours. No electricity means no communication, no internet, no cell phones, no television, no radio. No electricity means hospitals lose life support systems, dialysis machines, and surgical capabilities once backup generators run out of fuel. No electricity means banking systems crash, supply chains collapse, and the economic infrastructure that delivers food to cities ceases to function. We already have a preview of what smaller geomagnetic storms can do. In March 1989, a geomagnetic storm far weaker than the Carrington Event struck Earth. Within 90 seconds, the entire Hydro-Quebec power grid in Canada collapsed. 6 million people lost electricity for 9 hours, and that was considered a minor event compared to what the Sun is capable of producing. A 2013 study by Lloyd's of London, the world's leading insurance market, estimated that a Carrington-class event could cause $0.6 to $2.6 trillion in damage to the United States alone, with full recovery taking 4 to 10 years. Scientists at the Space Weather Prediction Center have warned that a worst-case solar storm could trigger not just infrastructure damage, but also panic buying, public unrest, and waves of misinformation, as society struggles to cope with the sudden loss of the technology it depends on. So how likely is this? This is where the numbers get uncomfortable. Historical records of geomagnetic storms, combined with ice core data and cosmogenic isotope measurements, suggest that the probability of a Carrington-class or stronger event is roughly 12% per decade. Let that number settle in your mind. 12% per decade. That means in any given 10-year period, there is roughly a 1 in 8 chance of a geomagnetic storm powerful enough to cause trillions of dollars in damage and potentially destabilize global infrastructure. And right now, we are at the worst possible point in the solar cycle for such an event to occur. The Sun operates on an approximately 11-year cycle of activity, oscillating between periods of low activity, called solar minimum, and periods of high activity, called solar maximum. During solar maximum, the Sun produces more sunspot, solar flares, and coronal mass ejections. Solar cycle 25, the current cycle, began in December 2019. The original prediction from the Solar Cycle Prediction Panel was for a relatively weak cycle, peaking at 115 sunspots in July 2025. Reality has dramatically exceeded that prediction. Solar cycle 25 has been far more active than forecast. The 13-month smoothed monthly sunspot number reached 156.7 in August 2024, already exceeding the predicted peak by a wide margin. Some scientists revised their predictions to a peak of 184, potentially already reached in 2024. Since early 2025, solar activity has been quieting somewhat, but the cycle is not over, and the risk of a major coronal mass ejection remains elevated. Now, here is what we can and cannot do about this threat. The Sun is monitored continuously by NOAA's Space Weather Prediction Center, NASA's fleet of solar observation satellites, and international partners around the world. Solar flares, which are bursts of electromagnetic radiation, reach Earth at the speed of light, giving us only 8 minutes of warning. But flares themselves are not usually the primary danger. The real threat is the coronal mass ejection, the massive cloud of magnetized plasma that follows. CMEs typically take 15 to 72 hours to reach Earth, depending on their speed. This means we generally have at least half a day of warning that a major CME is heading our way. But here is the problem. Even with that warning, shutting down an entire continental power grid is an enormous logistical and economic challenge. Utilities would need to disconnect transformers, which means deliberately cutting power to hundreds of millions of people. The economic cost of even a planned shutdown would be in the billions, and if the warning turns out to be a false alarm, the cost was borne for nothing. This creates a terrible decision calculus for the people responsible for making that call. Now, we are about halfway through this video, and I want to take a moment to acknowledge something. If you have made it this far, you are clearly someone who genuinely cares about understanding the science of our world and our universe, and I want you to know that I do not take that lightly. Videos like this one take an enormous amount of research, fact-checking, and writing, and the reason I am able to keep making them is because of viewers like you who subscribe, who hit the like button, and who leave comments that tell the algorithm this content matters. So, if you are enjoying this, if you are learning something, if this video is giving you a new perspective on the fragility and the beauty of our existence, please take a moment right now to subscribe and turn on notifications. Drop a comment telling me which threat we have discussed so far you find the most terrifying. Is it the asteroids, the sun, or the supervolcanoes? I am genuinely curious to see what you think. And stick around because what we are about to discuss next comes from far beyond our solar system, and it might be the most terrifying thing on this entire list. Let us leave our solar system behind and travel out into the galaxy, because there are phenomena out there in the cosmos so powerful, so violent, and so incomprehensibly energetic that they make asteroid impacts and solar storms look like firecracker compared to a nuclear bomb. I want to tell you about gamma-ray bursts. Since the Big Bang itself, 13.8 billion years ago, gamma-ray bursts are the most energetic explosions that have ever occurred in the universe. Let me give you a sense of the scale we are talking about. Our sun will burn for approximately 10 billion years, converting hydrogen to helium through nuclear fusion and radiating energy in every direction. In its entire lifetime, our sun will produce an almost inconceivable amount of energy. A single gamma-ray burst releases more energy in 10 seconds than our sun will produce in its entire 10 billion year life. 10 seconds versus 10 billion years. That is the scale difference we are dealing with. Gamma-ray bursts come in two varieties. Long-duration gamma-ray bursts, those lasting more than about 2 seconds, are produced when a massive star, typically 25 or more times the mass of our sun, reaches the end of its life and collapses. The core of the star implodes to form a black hole, and as material falls inward, two incredibly intense jets of energy are launched from the poles of the collapsing star. These jets punch through the outer layers of the dying star and shoot out into space like cosmic blowtorches of nearly unimaginable power. Short-duration gamma-ray bursts, lasting less than about 2 seconds, are produced by a different mechanism. They occur when two neutron stars, the super-dense remnants of exploded stars, spiral together and merge, or when a neutron star merges with a black hole. These mergers release a burst of gravitational waves, a flash of gamma radiation, and a cascade of heavy element production. In fact, most of the gold, platinum, and uranium in the universe, including the gold in any jewelry you might be wearing right now, was forged in the fires of ancient neutron star collisions. We detect gamma-ray bursts almost every day with orbiting telescopes, and they appear scattered randomly across the sky, coming from distant galaxies billions of light years away. At those distances, they are fascinating but harmless. But what would happen if a gamma-ray burst occurred much closer to home? What if one went off within our own galaxy, within a few thousand light years of Earth, with its jet pointed directly at us? The effects have been modelled extensively by astrophysicists, and the results are genuinely nightmarish. A gamma-ray burst within approximately 6,000 to 10,000 light years, whose jet was aimed at Earth, would unleash a torrent of high-energy photons that would strike the upper atmosphere with devastating effect. The gamma rays would ionize the nitrogen and oxygen molecules in the stratosphere and mesosphere, triggering a cascade of chemical reactions that would produce enormous quantities of nitrogen oxides. These nitrogen oxide compounds are extraordinarily efficient at destroying ozone. The ozone layer, that thin shield in the upper atmosphere that protects all surface life from the sun's lethal ultraviolet radiation, would be catalytically destroyed, not reduced, destroyed. With the ozone layer gone, the full force of the sun's ultraviolet radiation would reach the surface. UVB and UVC radiation, which are normally almost completely absorbed by the ozone layer, would flood the surface of the planet. This radiation damages DNA, causes mutations, kills cells, and is lethal to many organisms at high enough doses. Phytoplankton, the tiny photosynthetic organisms that live in the upper layers of the ocean and produce roughly half of all the oxygen on Earth, would be devastated. These organisms are the foundation of the marine food web. If they die, everything that depends on them, from zooplankton to fish to whales, follows. On land, plants would suffer DNA damage, reduced photosynthesis, and increased mutation rates. Animals would experience increased cancer rates, reproductive failure, and immune system damage. But that is not all. The nitrogen oxides produced in the atmosphere would have additional effects. Nitrogen dioxide is a brown-colored gas, and in sufficient concentrations, it would create a visible brown haze in the sky, reducing the amount of sunlight reaching the surface. This would compound the damage by reducing photosynthesis further and potentially triggering climate cooling. Additionally, the nitrogen oxide compounds would combine with water in the atmosphere to form nitric acid, which would fall as acid rain, damaging ecosystems, freshwater supplies, and soils. The overall effect would not be instantaneous annihilation. It would be something arguably worse, a slow, agonizing ecological collapse, playing out over months and years. Food chains would disintegrate from the bottom up. Ecosystems that had evolved over millions of years would unravel. And the estimated result, based on modeling by astrophysicists including Adrian Mellott and colleagues, is that a nearby gamma-ray burst could trigger a mass extinction, eliminating 50% or more of all species on Earth. Has this actually happened in Earth's past? There is a hypothesis, and I want to be very clear about its status as a hypothesis, that a gamma-ray burst may have contributed to the late Ordovician mass extinction approximately 445 million years ago. This was the second largest mass extinction in Earth's history, with approximately 85% of marine species going extinct. A 2004 study by Mellott and colleagues, published in the International Journal of Astrobiology, pointed out several features of this extinction that are consistent with the gamma-ray burst scenario. The extinction was geologically sudden. It preferentially affected organisms living in shallow water, which would have been more exposed to increased ultraviolet radiation than deep-water organisms. And there is evidence consistent with ozone depletion during that period. However, and this is critically important, there is no unambiguous direct evidence that a gamma-ray burst actually occurred at that time. No smoking gun has been found in the rock record. Glaciation and dramatic sea level changes are the more commonly accepted primary causes of the late Ordovician extinction. The gamma-ray burst hypothesis has not been confirmed, but it has also not been ruled out. It may have been a contributing factor to an extinction that had multiple causes. So should we be worried about a gamma-ray burst happening in our cosmic neighborhood? Let me tell you about a star system that once made headlines as a potential Death Star aimed at Earth. WAR 104 is a Wolf-Rayet binary star system located approximately 2,580 light-years from Earth. Wolf-Rayet stars are massive, luminous, dying stars in the final stages of their evolution before they explode as supernovae. They are among the hottest and most energetic stars in the galaxy. When 104 was first discovered and imaged, its spiral pinwheel pattern of stellar wind, created by the interaction of the two stars in the binary system, was breathtaking. But astronomers noticed something deeply unsettling. The orientation of the spiral suggested that the star system's rotational axis might be pointing directly at Earth. If 104 produced a gamma-ray burst when it exploded, and if its jet was indeed aimed at us, the consequences could be severe even at a distance of over 2,500 light-years. This made international headlines. The pinwheel Death Star, some journalists called it. But subsequent observations, including detailed studies using the Keck Observatory, published as recently as 2025, have provided substantial relief. The axis of WR104 appears to be tilted approximately 30 to 40 degrees away from Earth's line of sight, which would place us well outside the narrow cone of any potential gamma-ray burst jet. Furthermore, gamma-ray bursts are primarily associated with galaxies that have low metallicity, meaning they contain fewer heavy elements. The Milky Way is a relatively high metallicity galaxy, which makes it less likely that any of its stars would produce a gamma-ray burst in the first place. The current scientific consensus is that WR104 is almost certainly not a threat to Earth, but it taught us to take the possibility seriously and to study it rigorously. While we are discussing cosmic explosions, I want to tell you about a related threat that has received increasing scientific attention in recent years, the kilonova. When two neutron stars merge, they produce not only a short gamma-ray burst, but also a broader explosion called a kilonova, which bathes the surrounding space in electromagnetic radiation, gravitational waves, and a hail of newly formed heavy elements. In 2017, the LIGO and Virgo gravitational wave detectors made history by detecting gravitational waves from a neutron star merger for the first time, an event designated GW170817. Telescopes around the world observed the resulting kilonova, and for the first time, humanity witnessed the birth of heavy elements like gold and platinum in real time. It was one of the most remarkable scientific observations ever made. But a 2024 study published in the Astrophysical Journal raised the question of what a kilonova would do to a nearby planet like Earth. The researchers found that within approximately 36 light-years, the cosmic rays accelerated by a kilonova remnant could strip Earth's ozone layer for thousands of years, far longer than the initial burst of radiation. Within approximately 6.5 light-years, the direct radiation could be lethal. The good news is that there are no known neutron star binary systems close enough to threaten Earth in the foreseeable future. The bad news is that our catalogue of such systems may not be complete. Neutron stars are small, faint, and extremely difficult to detect unless they are actively pulsing or accreting matter. Now, I want to tell you about something that actually happened. Not a theoretical threat, not a model, not a prediction, but a real event that occurred on December 27th, 2004. On that date, instruments aboard virtually every X-ray and gamma-ray satellite in orbit around Earth suddenly recorded an overwhelming flood of radiation coming from a single point in the sky. Many detectors were saturated, overwhelmed by the intensity of the signal. What had happened was this. A magnetar, designated SGR 1806-20, located approximately 50,000 light-years from Earth on the far side of the Milky Way galaxy, had erupted. A magnetar is a type of neutron star with the most powerful magnetic field known in the universe, trillions of times stronger than Earth's magnetic field. SGR 1806-20 had released what astronomers call a giant flare, and in just 0.2 of a second, it radiated more energy than our Sun produces in 250,000 years. The radiation traveled across the entire galaxy and struck Earth. Despite the immense distance of 50,000 light-years, the effects on our planet were measurable. The radiation physically compressed Earth's magnetosphere. It ionized the upper atmosphere on the night side of the planet, raising the ionization level to daytime values. It disrupted some satellite communications. As Scientific American reported, on the 20th anniversary of this event, the magnetar's epic tantrum made our planet ring like a bell from tens of thousands of light-years away. Let me make sure that sinks in. An event that lasted 0.2 of a second, occurring 50,000 light-years away, on the opposite side of the galaxy, measurably affected Earth's atmosphere and magnetic field. Now imagine what would happen if a magnetar flare occurred not 50,000 light-years away, but a few hundred or a few dozen. A magnetar within a few light-years whose flare was directed at Earth could strip the ozone layer, cause mass radiation exposure, and potentially sterilize the hemisphere facing the burst. The saving grace is that the nearest known magnetar is thousands of light-years away, and there are estimated to be only about 30 known magnetars out of the roughly 30 million neutron stars in the Milky Way. The probability of a dangerously close magnetar flare is extremely low, but the 2004 event proved that these objects can reach across the galaxy and touch our world. Let me now shift our attention to something that you can actually see with your own eyes on any clear winter night. Look toward the constellation Orion and find the bright reddish star that marks the hunter's shoulder. That star is Betelgeuse, and it is dying. Betelgeuse is a red supergiant, one of the largest stars visible to the naked eye. It is approximately 650 to 700 light-years from Earth. If you could place Betelgeuse at the center of our solar system, its surface would extend beyond the orbit of Mars and might reach as far as Jupiter. It is a star of truly monstrous proportions, and it is in the final stages of its stellar life. Betelgeuse has burned through its hydrogen fuel, then its helium, and it is now fusing heavier and heavier elements in its core. Eventually, perhaps within the next 100,000 years, perhaps much sooner, the core will run out of fusible material and collapse. Betelgeuse will explode as a supernova. In late 2019 and early 2020, Betelgeuse underwent a dramatic and unprecedented dimming event. Its brightness dropped by roughly a factor of 3 over the course of a few months. Astronomers and the public alike speculated wildly. Was Betelgeuse about to explode? The excitement was palpable. But subsequent observations revealed a more mundane explanation. Betelgeuse had ejected a massive cloud of dust from its surface, and this dust temporarily obscured the star from our perspective. The Great Dimming, as it came to be called, was fascinating from a stellar physics standpoint, but did not indicate that an explosion was imminent. When Betelgeuse does eventually explode, it will be the most spectacular astronomical event in recorded human history. It will become as bright as the full moon, clearly visible during daytime, and it will remain at that brightness for weeks to months before gradually fading. It will be visible to every person on Earth. But here is the important part. At a distance of 650 plus light years, Betelgeuse is well beyond the danger zone for a supernova. A supernova needs to be within roughly 25 to 50 light years of Earth to cause significant damage to the ozone layer and biosphere. At 650 light years, Betelgeuse's supernova will be a breathtaking spectacle and nothing more. No ozone depletion, no harmful radiation reaching the surface, no gravitational effects, nothing dangerous. Just the most incredible light show any human being has ever witnessed. However, this raises a legitimate question. If Betelgeuse is safe, are there any stars close enough to us that could go supernova and actually cause harm? The closest known supernova candidate is IK Pegasi, a binary star system approximately 154 light-years from Earth. One of its components is a white dwarf that could theoretically become a Type 1 supernova if it accumulates enough mass from its companion star. But at 154 light-years, this is still considered safely outside the lethal range, and the conditions necessary for IK Pegasi to reach supernova are not expected to be met for millions of years, if they are ever met at all. Based on our current understanding of the stellar neighborhood, there are no known stars close enough to Earth that are expected to go supernova in a timeframe that should concern us. But our catalogues are not perfect, and there may be stellar systems we have not yet fully characterized. There is another phenomenon that I believe deserves serious attention, and it is not something happening in outer space. It is happening right here, on our own planet, right now, and it has been going on for decades. I am talking about the weakening of Earth's magnetic field. Earth's magnetic field is generated by the motion of liquid iron in the planet's outer core, a process scientists call the geodynamo. This molten iron, heated by the decay of radioactive elements and the residual heat from Earth's formation, circulates in complex patterns driven by the planet's rotation. These currents of liquid metal generate electrical currents, which in turn produce the magnetic field that extends far out into space, creating the magnetosphere. The magnetosphere is not just a curiosity for compass makers. It is, quite literally, the shield that makes life on Earth possible. It deflects the solar wind, a continuous stream of charged particles blasting outward from the sun at hundreds of kilometers per second. Without the magnetosphere, the solar wind would gradually strip away Earth's atmosphere, particularly the lighter gases like hydrogen and oxygen. This is almost certainly what happened to Mars. Mars once had a magnetic field, and when it lost that field approximately 4 billion years ago, the solar wind slowly eroded its atmosphere, turning it from a planet with liquid water and a thick atmosphere into the cold, barren desert we see today. But Earth's magnetic field is not static or stable. It changes constantly, shifting in strength and configuration over timescales ranging from decades to millions of years. And right now, something is happening that has the attention of the scientific community. The South Atlantic Anomaly is a large region over South America and the Southern Atlantic Ocean where Earth's magnetic field is significantly weaker than anywhere else on the planet. This anomaly was first identified in the 19th century, and since then, it has been growing. Data from the European Space Agency's Swarm satellite constellation, which has been monitoring the magnetic field from orbit since 2013, shows that the South Atlantic Anomaly has expanded dramatically. As of February 2026, ESA reported that the anomaly has grown to nearly half the size of the South Atlantic Ocean. Within this region, the weaker magnetic field allows more charged particles from the solar wind and cosmic rays to penetrate closer to Earth's surface. The effects are already being felt. Satellites passing through the South Atlantic Anomaly experience increased radiation damage to their electronics. Astronauts aboard the International Space Station report seeing brief flashing lights when they transit the anomaly, caused by high-energy particles striking the retinas of their eyes, a phenomenon related to Cherenkov radiation. Satellite operators routinely shut down sensitive instruments when their spacecraft pass through this zone to prevent damage. But the South Atlantic Anomaly may be more than just a localized weakness. It may be a harbinger of something much larger. Earth's magnetic field has been weakening overall by approximately 5% per century for the last 200 years. Some scientists believe this weakening could be an early sign of an approaching magnetic pole reversal. Magnetic pole reversals are not hypothetical. They are a well-documented feature of Earth's geological history. The rock record shows that Earth's magnetic poles have reversed hundreds of times over the past several hundred million years, with the North Magnetic Pole becoming the South Magnetic Pole, and vice versa. The average time between reversals is roughly 200,000 to 300,000 years. The last full reversal, known as the Brunhes-Matuyama reversal, occurred approximately 780,000 years ago. This means that, statistically speaking, we are overdue. Though, as with Yellowstone, it is important to note that the magnetic field does not follow a predictable schedule. What would a reversal actually mean for life on Earth? We have some clues from the geological record. Approximately 42,000 years ago, Earth experienced what scientists call the Laschamp excursion, a temporary partial reversal in which the magnetic field strength dropped to about 6% of its current value before recovering. A 2021 study linked this event to significant environmental changes. With the magnetic field so weak, cosmic radiation reaching the surface increased dramatically. The ozone layer was damaged. Ultraviolet radiation levels at the surface increased. The study suggested possible connections to changes in atmospheric chemistry, climate shifts, and even the extinction of the Neanderthals, our closest human relatives, who disappeared from the fossil record around this time. The researchers also speculated that the increased radiation may have driven early modern humans to seek shelter in caves more frequently, potentially contributing to the explosion of cave art that appeared around this period. During a full reversal, the process would not happen overnight. It takes approximately 1,000 to 10,000 years for the poles to swap completely. During this transition period, the magnetic field does not simply disappear. Instead, it becomes chaotic and multipolar, with several weaker north and south poles scattered across the globe, rather than the simple dipole field we have today. This weakened, chaotic field would provide substantially less protection from solar radiation and cosmic rays. The effects would include increased radiation exposure for all surface life, potential ozone layer damage during solar storms, degradation and failure of satellites due to increased radiation in near-Earth space, disruption of navigation systems that rely on the magnetic field, and increased cancer rates and genetic mutation rates in surface-dwelling organisms. NASA has been clear that a reversal happens over hundreds or thousands of years, and is not a sudden flip. The field does not drop to zero. It becomes complex and weaker, but the consequences, even spread over millennia, would be significant for a technologically dependent civilization. Now I want to take you into an even more exotic territory. Let us talk about the threats we cannot see coming, because they are literally invisible. I want to tell you about rogue black holes. When a massive star explodes as a supernova, the core can collapse to form a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. Most black holes that we know about are anchored in place, orbiting in binary systems with companion stars, or sitting at the centers of galaxies. But not all of them stay put. Gravitational interactions in dense stellar environments can eject black holes from their host systems, sending them careening through the galaxy at high speeds. These are rogue black holes, and they are, quite literally, invisible. A black hole does not emit light. It does not reflect light. The only way to detect one is through its gravitational effects on nearby matter and light, a phenomenon called gravitational lensing, where the black hole's gravity bends the light from background stars, distorting their apparent positions. Astronomers estimate that there may be hundreds of millions to billions of rogue black holes wandering through the Milky Way. The nearest known black hole is Gaia BH1, discovered in 2022 using data from the European Space Agency's Gaia satellite. It is approximately 1,560 light-years from Earth. It was detected because of its gravitational effect on a companion star, not because anyone could see the black hole itself. What would happen if a rogue black hole entered our solar system? The answer depends on how close it came and how massive it was. A stellar mass black hole, say 10 times the mass of the Sun, passing through the outer reaches of our solar system could gravitationally perturb the Oort cloud, the vast shell of icy bodies that surrounds the solar system at a distance of roughly 1 to 2 light-years. A gravitational disturbance of the Oort cloud could send a shower of comets into the inner solar system, dramatically increasing the probability of a cometary impact on Earth over the following millions of years. If the rogue black hole passed closer, through the region of the planets, the gravitational effects could be catastrophic. Planetary orbits could be destabilized. Earth could be pulled out of the habitable zone, either closer to the Sun, triggering a runaway greenhouse effect, or farther away, causing a global freeze. The Moon could be stripped away from Earth. Other planets could be ejected from the solar system entirely. And in the extraordinarily unlikely scenario that a rogue black hole actually collided with Earth, the planet would simply be consumed. Matter would spiral inward past the event horizon and be compressed to a singularity. Earth would cease to exist in any recognizable form. But I must be very clear about the probability here. The chances of a rogue black hole entering our inner solar system are vanishingly small. Despite the estimated hundreds of millions of rogue black holes in the galaxy, space is overwhelmingly empty. The distances between stars and between any given point in space and the nearest black hole are almost inconceivably vast. The probability of a rogue black hole coming close enough to significantly affect Earth has been estimated at less than 1 in 10 trillion per billion years. This is a theoretical possibility, not a practical concern. A related but even more exotic possibility involves rogue planets, planets that have been ejected from their parent star systems and drift through interstellar space. The Milky Way may contain billions of rogue planets, perhaps more rogue planets than there are stars. If a rogue planet entered our solar system, it could gravitationally disrupt planetary orbits, potentially altering Earth's position relative to the Sun. However, the probability of this happening is similarly negligible. Astronomers estimate that a rogue planet passing through the inner solar system occurs roughly once every 100 billion years. Given that the universe is only 13.8 billion years old, this is not something that keeps astrophysicists up at night. I also want to mention, briefly, the concept of primordial black holes, because some fascinating new research has been published on this topic. Primordial black holes are hypothetical tiny black holes that may have formed in the extreme conditions of the Big Bang, when the density of the early universe was so high that random fluctuations could have compressed small regions of space into black holes. These would not be stellar mass black holes, but could range in size from less than an atom to many times the mass of a mountain. A December 2024 study from the University at Buffalo explored the possibility that primordial black holes could be hiding inside planets, or even inside everyday objects here on Earth, their presence undetectable by current technology. The idea that a subatomic black hole might pass through your living room without you ever knowing is unsettling, but the scientific consensus is clear. There is currently no evidence that primordial black holes exist at any size, and even if they do, the probability of one interacting with Earth in a harmful way is so remote as to be effectively zero. This remains a fascinating area of theoretical physics, not a practical threat assessment. Now, I want to take you to the absolute edge of physics, to a concept so terrifying that some physicists have called it the ultimate cosmic catastrophe. I want to tell you about vacuum decay. To understand vacuum decay, we need to start with the Higgs field. In 2012, physicists at CERN's Large Hadron Collider confirmed the existence of the Higgs boson, a particle associated with the Higgs field. The Higgs field is a quantum field that permeates all of space. It is everywhere right now, filling the room you're in, filling the space between galaxies, filling every cubic centimeter of the universe. And it is this field that gives fundamental particles their mass. Without the Higgs field, electrons would be massless, atoms could not form, chemistry would not work, and you would not exist. The current state of the Higgs field determines the fundamental laws of physics as we experience them, the masses of particles, the strengths of the fundamental forces, the behavior of atoms and molecules. Here is the terrifying part. Measurements of the Higgs boson mass, approximately 125.25 gigaelectron volts, combined with measurements of the top quark mass, suggest that the Higgs field may not be in its lowest possible energy state. Instead, it may be in what physicists call a metastable state, or a false vacuum. Think of it this way. Imagine a ball resting in a small valley partway up a mountainside. The ball is stable. If you give it a small push, it rolls back to the bottom of the valley. It looks like it is at the lowest point, but there is a deeper valley farther down the mountain. The ball is not at the true lowest point, the global minimum. It is at a local minimum, a temporary resting place. And if something gave the ball a big enough push, or if quantum mechanics allowed the ball to tunnel through the ridge between the two valleys, it would roll down to the true lowest point and never come back. This is what a false vacuum hypothesis suggests about our universe. The Higgs field is resting in a valley that looks stable, but there may be a deeper, lower energy state that it could fall into. If this happened, if the Higgs field quantum tunneled from its current metastable state to the true vacuum state, the consequences would be absolute. A bubble of true vacuum would form at the point where the transition occurred. Inside this bubble, the Higgs field would be at a different energy level, and the laws of physics inside the bubble would be fundamentally different from the laws of physics outside it. The masses of fundamental particles would change. The strengths of the forces holding atoms together would change. Atoms, as we know them, could not exist inside the bubble. Chemistry, biology, matter itself as we understand it, would not function, and this bubble would expand at the speed of light. Nothing can outrun it. Nothing can stop it. You cannot detect it coming because it moves at the ultimate speed limit of the universe. Information about its existence reaches you at exactly the same moment the bubble itself does. There is no warning. There is no defense. There is no escape. Everything the bubble touches is not destroyed in the conventional sense. It is rewritten. The fundamental nature of matter is changed. It is not an explosion. It is not a fire. It is not radiation. It is the erasure of the physics that makes your existence possible. In April 2026, physicists at the Chinese Academy of Sciences made headlines by using a tabletop ring of atoms to simulate the process of false vacuum decay for the first time experimentally. Using a quantum simulator, they demonstrated the quantum tunneling process by which a metastable state can decay to a lower energy state. This experiment did not create any danger. It was modeling the physics at incredibly tiny scales, but it was the first time the dynamics of vacuum decay had been observed in a controlled laboratory setting, and it provided important validation of the theoretical framework. Let me be very clear about the probability of vacuum decay. It is, by any practical measure, effectively zero. The expected time for spontaneous vacuum decay is estimated to be many, many orders of magnitude longer than the current age of the universe. We are talking about timescales so long that numbers lose their meaning. The universe could exist for trillions upon trillions upon trillions of years before this happens, if it happens at all. Some physicists argue that the metastable state, if it exists, is so stable that it will effectively last forever. Others point out that we are not even certain the universe is in a metastable state. The measurements of the Higgs boson and top quark masses place us right on the boundary between a stable and metastable vacuum, and the uncertainty in those measurements means we might actually be in a stable vacuum after all. But I include vacuum decay in this video because, despite its infinitesimally small probability, it represents the single most complete and irreversible form of destruction that the laws of physics allow. If it happened, there would be no survivors, no remnants, no archaeological record. The universe, or at least the portion of it, touched by the bubble, would simply become something fundamentally different. And if the transition has already occurred somewhere in the distant reaches of the universe, a bubble could be racing toward us right now at the speed of light, and we would never know until the instant it arrived. Now, after all of this discussion of catastrophic possibilities, I want to ground us in something certain. Not probable, not hypothetical, certain. I want to talk about the long-term fate of our planet, the things that physics and astronomy guarantee will happen, no matter what we do. Our sun is a middle-aged star. It is approximately 4.6 billion years old, and it has roughly another 5 billion years of hydrogen fuel remaining in its core. But the sun is not going to wait 5 billion years to become dangerous. Stars like our sun gradually increase in luminosity over their lifetimes. As the sun ages, it slowly burns hotter and brighter. In approximately 1 billion years, the sun's luminosity will have increased by about 10%. This does not sound like much, but the effects on Earth will be catastrophic. The increased solar energy will accelerate the evaporation of water from the oceans. More water vapor in the atmosphere means a stronger greenhouse effect, which traps more heat, which causes more evaporation, which increases the greenhouse effect further. This is called a runaway greenhouse effect, and it is what happened to Venus. Within about 1 billion years, Earth's oceans will have evaporated. The surface temperature will rise to levels incompatible with any known form of life. Earth will become a scorched, dry, lifeless world. This is not a possibility. This is a certainty, based on well-understood stellar physics. In approximately 5 billion years, the Sun will exhaust its hydrogen fuel entirely. The core will contract and heat up, and the outer layers will expand enormously. The Sun will swell into a red giant, growing so large that its surface will engulf the orbit of Mercury and Venus. Whether it will actually reach Earth's current orbit is debated. Some models suggest it will. Others suggest that the Sun's mass loss as it expands will cause Earth's orbit to move outward, potentially keeping it just beyond the red giant's reach. Either way, the intense radiation from the bloated Sun will sterilize the surface and boil away any remaining atmosphere. Eventually, the Sun will shed its outer layers as a beautiful planetary nebula, a shell of glowing gas expanding into space, and the core will collapse into a white dwarf, a dense, cooling ember about the size of Earth, but with roughly half the Sun's mass. The solar system as we know it will be gone. On a similar timescale, approximately 4.5 billion years from now, our galaxy, the Milky Way, will collide and merge with the Andromeda galaxy. Andromeda is currently approaching us at about 110 kilometers per second. The collision will not be the dramatic smash that you might picture. Galaxies are mostly empty space, and the distances between individual stars within a galaxy are so vast that actual stellar collisions will be extremely rare. Instead, the two galaxies will pass through each other, gravitationally distort each other, and eventually merge into a single larger elliptical galaxy that astronomers have already nicknamed Milkdromeda. Our solar system will almost certainly survive this merger intact, though its position within the resulting galaxy will be very different from where it is today. The night sky, however, would be utterly transformed, and on even longer timescales, Earth's own internal processes will wind down. The heat engine that drives plate tectonics, the motion of continental plates, the creation of mountains, the recycling of carbon through volcanism, the generation of the magnetic field, all of this is powered by heat from the Earth's interior. This heat comes from the decay of radioactive elements, and from the residual heat of Earth's formation. But this heat is finite. Over billions of years, the Earth's interior is slowly cooling. Eventually, plate tectonics will cease. When that happens, the carbon-silicate cycle, the geological thermostat that has regulated Earth's climate for billions of years by recycling carbon dioxide between the atmosphere and the rock, will stop. Without this cycle, the planet will lose its ability to regulate its own climate. And without the convection in the outer core that drives the geodynamo, the magnetic field will fade, leaving the planet exposed to the solar wind. Earth will, in the very long run, become a dead world, much like Mars is today. But all of these long-term fates are exactly that. Long-term. They unfold over billions of years. They are the inevitable destiny of a planet orbiting a mortal star in a changing universe. What concerns us in this video are the threats that could disrupt our world on much shorter timescales, within our lifetimes, within our children's lifetimes, within the next few centuries or millennia. So let me put everything we have discussed into perspective by ranking these threats by their realistic probability, starting with the most likely and working down to the least likely. The most likely near-term threat is a severe solar superstorm of Carrington-class intensity. With an estimated probability of roughly 12% per decade, this is not a fringe risk. It is a mainstream, well-studied threat that organizations like NOAA, NASA, Lloyd's of London, and the National Academy of Sciences have all warned about. A Carrington-class event would not destroy the planet. Earth itself would be fine, but our technological civilization, our power grids, our satellites, our communication systems, our interconnected global economy, these could suffer damage on a scale that takes years to recover from. The next most likely threat is a supervolcanic eruption. The probability of a VEI 7 or 8 eruption in any given year is very low, roughly 1 in 730,000 for Yellowstone specifically. But there are multiple supervolcanic systems around the world, and the cumulative probability across all of them is somewhat higher. A super eruption would not destroy the planet, but it could plunge civilization into a volcanic winter lasting years, devastate agriculture, and cause famine and social upheaval on a global scale. Significant asteroid impacts fall next on the probability scale. Small impacts, Chelyabinsk-class events, occur roughly once per century. They can cause localized damage and injuries, but are not civilization-threatening. Football field-sized impacts capable of destroying a city occur every few thousand years, and Chicxulub-class events, true planet killers, occur roughly once every 100 million years. The important thing to understand about asteroid risk is that unlike most other threats on this list, it is the one we are most actively working to prevent. DART proved that deflection is possible. NEO Surveyor will close the detection gaps. Sentry monitors the skies continuously. We are not helpless against asteroids, though our capabilities are still limited. A nearby supernova is extremely unlikely to occur within the next several million years. No known stellar candidates are close enough to pose a threat on any human-relevant timescale. A gamma-ray burst hitting Earth is estimated to occur perhaps once every several hundred million years, and the probability in any given century is negligible. Magnetic pole reversal is almost certain to happen within the next few 100,000 years, but the process takes thousands of years to unfold, giving civilization time to adapt. Assuming we are still around and technologically capable, a rogue black hole or rogue planet entering our inner solar system is essentially zero probability on any human-relevant timescale. And vacuum decay, while theoretically possible, has a probability so low that it is effectively indistinguishable from zero. So, where does this leave us? After everything we have discussed, after the asteroids and the solar storms, and the supervolcanoes and the gamma-ray bursts, and the dying magnetic field, and the rogue black holes, and the very fabric of space itself potentially being unstable, where does that leave us? It leaves us exactly where we have always been, on a small rocky planet, orbiting an ordinary star, in the suburbs of an ordinary galaxy, in a universe that is vast and ancient and beautiful and utterly completely indifferent to our survival. The universe did not create us on purpose. It did not place us here with intent. We are an accident of chemistry, of physics, of 4.5 billion years of geological and biological processes that had no goal and no plan. And the forces that could destroy us, the asteroids, the eruptions, the radiation bursts, the stellar explosions, they are not evil, they are not malicious. They are simply the natural processes of a cosmos that operates according to its laws without regard for the tiny beings who happen to have evolved on one small world. But here is what I find truly remarkable about our situation. Earth has been through all of this before. Not the theoretical threats, the real ones. Earth has been struck by asteroids large enough to cause mass extinctions. It has endured supervolcanic winters. It has weathered the loss of its magnetic shielding during excursions and reversals. It has been bathed in radiation from distant cosmic events. And through every single one of these catastrophes, life survived. Not all of it, not even most of it, in the worst cases. But enough. Enough organisms in enough protected niches to rebuild, to diversify, to evolve, to eventually produce, after billions of years of trial and error and catastrophe and recovery, a species capable of understanding its own precarious position in the cosmos. That species is us, and we are something genuinely new in the history of this planet. For 4.5 billion years, life on Earth was reactive. It could only endure what the universe threw at it, and hope that enough survived to carry on. The dinosaurs could not build telescopes. The trilobites could not launch spacecraft. The ancient bacteria that survived the earliest asteroid bombardments did so through sheer biochemical resilience, not through knowledge or planning. But we can see the asteroids coming. We have mapped the near-Earth object population. We have visited asteroids and brought samples back to our laboratories.